Today we're taking a look at Chapter 10 on correlation and regression, and in Section 10-2 we'll take specifically a look at correlation. And correlation is something we discuss when sample data occur in pairs and we determine that there is a relationship between the pairs. So we say if there is a relationship between the data pairs, we call it correlation. Correlation exists between two variables when one of them is related to the other in some way. And the assumptions we're making in this case are, first of all, the data pair XY sample is a random sample. The pairs of XY data have a bivariate normal distribution. That means for a fixed value of X, the distribution is bell-shaped, and for a fixed value of Y, the X distribution is bell-shaped. Note that since we are working with ordered pairs here, we will graph the ordered pair XY as coordinates on the Cartesian coordinate plane. In statistics, we refer to this as a scatter plot. And so first we want to look at some different scatter plots showing different kinds of correlation. As we look at this scatter plot, we'll notice that the lines pretty much fall in a straight line. If they fall in a straight line, we have what is called as perfect linear correlation. And if you notice, if we think about rise over run, up and to the right, we have a positive slope. So we refer to this as a positive linear correlation. See if I can get my ink tools to open up here. There we go. So this one's positive because the line is going in a positive direction. Now the second graph shows again positive linear correlation. However, you'll notice that the dots are not all on a straight line, so some of them are a little bit off. Again, that's positive. No linear correlation would occur when the dots are just scattered everywhere. And if we want to talk about negative linear correlation, the dots would go, for positive would be in a very straight line. For negative, they would be scattered about, again, in a negative direction. There are additional scatter plots in the textbook, and I would suggest that you look through those. Now, we will be using technology as we work with scatter plots, particularly with correlation and regression. And the reason we use this is because the formulas are very complicated, and if we put them in the calculator will do the number crunching. So what you'll notice is that I say do not sort X and Y columns separately since they are data pairs. You want to keep the pairs together, so don't do any sorting. Don't do any sorting on these columns. All right, the formula for the linear correlation coefficient R, and this is the value that measures the strength of the linear relationship between the paired X and Y values in a sample, is this ugly looking character right here. So we have to take the number of data pairs, that's our N, the sum of the product of the X and the Y, minus the sum of the X times the sum of the Y. We divide that whole thing by the square root of N, again the number of data pairs, times the sum of the X squared values, minus the sum of the X's, that quantity squared, all of that's in a radical, times inside another radical, N times the sum of the Y squares, minus the sum of the Y's, that value squared. And again, that's all inside a radical. So you can see it's very messy to have to calculate by hand. So if the absolute value of the computed value of R exceeds the value in table A6, conclude that there is a significant linear correlation. Otherwise, there is not enough evidence to support the conclusion that there is significant linear correlation. And so if no value is given for alpha, assume that it's alpha equal to 0.05. That will be our very first column. And I'll try to show you that table. Okay, now the properties of the linear correlation coefficient. R will always be a value between -1 and +1 inclusive. If we have a negative, we have perfect negative linear correlation. If we have a +1, we have perfect positive linear correlation. Anything in between that gives us, may give us correlation, linear correlation, and it may not. We have to check that table A6. The value of R does not change if all the values of either variable are converted to a different scale. So if you changed inches into centimeters, it wouldn't matter. The value of R is not affected by the choice of X or Y. So if we interchange all the X and Y values, the value of R will still be the same. The R measures the strength of the linear relationship. It is not designed to measure the strength of a relationship that is not linear. And let me comment here, it's possible when you're looking at to have something that comes out looking like it might be quadratic. For example, here we see the shape of a parabola. We could also have one that's exponential and so forth. So linear is not the only type of correlation. It's the only one we're studying, but there are other types of correlation. R squared is called the coefficient of determination. So if you take your R, calculate it using that formula from the previous page, and you square it, that gives the coefficient of determination. It represents the proportion of variation in Y that is explained by the linear relationship between X and Y. And so we're going to look at the Math 120 grades as an example. Finally, common errors involving correlation. A common error is to conclude that correlation implies causality. Just because two variables both increase at the same time does not mean that the one caused the other. So correlation does not imply causality. Very important to remember. Another area is when you work with data that's based on averages. The averages tend to inflate the correlation coefficient. Third error is to conclude that there's no correlation between two variables when we're checking R. There may be no linear correlation between the two variables, but there may be quadratic, as we spoke of up above, or some other type of correlation between the variables. And we're going to be looking at an example I have of Math 120 grades to talk about this correlation in another recording.